Session is being recorded. Hopefully my audio is working now, right? Okay. It says it's working. Last time we were able to get the audio to work. It wouldn't record for whatever reason. Okay. So we left off last week talking about the different queuing methods for quality of service. Okay. So let's kind of look the components that you're working with. Okay, in quality of service, the first kind of component is classification and marking. So classification and marking. So one of the things I want to talk about is trust in quality of service. They cover it well in the book. They don't cover it so well in the slides. So it doesn't pertain to this slide here. At what point in the network do you begin trusting your marking? We're going to talk more about marking here in a few of like what we're talking about. What is marking? How are we marking the traffic? Classification is how we classify the traffic into different groups. Marking is how we validate, how we mark the actual traffic so we know it's a member of a particular class. Okay? So in marking, at what point are we going to trust this? For instance, if I trust the marking from the PC, then someone who knows what they're doing can just go in here and change the Diffserv values, the DCSP values. It's either DSCP or DCSP. I can't remember what's sort of their acronym. It's for the Diffserv of Flags, right? So who do you set those? You can go into your NIC and set those here. So you could theoretically, if you know what you're doing, you could set it as AF. Or you could set it as EF. EF is what voice traffic gets in Diffserv. AF is essentially, I forget the acronym for it, but EF and AF. EF is guaranteed. You just have one queue and it's voice. Voice always goes EF. Well, I could mark my traffic at the PC as EF, and it would cause all the devices to treat it with the highest priority. Okay, so at what point do we set our trust point of when these markings are going to be trusted and when they're added? So there's a couple differences where we can do that. We typically, it's going to be, if it's an IP phone, it's at the phone as a trust point. We're feeding details down to the phone, and the phone is installing marks onto the frames or the packets from the phone on. And it can mark the stuff coming from this differently than it marks its own stuff. Okay, so that's one point that we can have. The other point is the switch. So here's the difference. We always make the trust point of where we begin to trust these markings when we see them and utilize them. We begin that trust point at equipment we control, not the people. Okay? The person that uses this usually has administrative access on their computer. That's very, very common. It just saved my life as the administrator a lot of work of having to go and make sure everything that requires administrative access has that especially set up for it. Or just give them local administrative access on their machine and put everything else on the server. If they toast their machine, just re-image it and they're up and running in like an hour. Okay, that's how a lot of times we do it. It's just for ease of use. Remember how you can't print and do other stuff? We've got to get someone to, we don't want to do that in the real world too much. Okay? So by doing it at the phone, doing it at the switch, it's something that we directly control as administrators. They have no way to program the phone or anything. The phone is programmed from the network. Okay, it downloads its a configuration file from a TFTP server when it boots, and we give all that information through DHCP and CDP or LLDP to talk to the phones, right? So think about where we're going to begin accepting the marks. That's our trust point in quality of service. And everything that's going to work with our marks has to trust that those marks are legitimate and that they were added at the correct trust point. So and trust point's a term that you're going to hear in a lot of different things where we have trust points. We use that in encryption and security. But in quality of service, we have trust points. That's going to be your trust point for your QoS marking is going to be your phone or your switch. So how are we going to mark traffic on a switch? How do we go about doing that? Well, think about marking is all about ACLs. Classification, so there's a couple different ways to do classification. Okay, we can do classification through ACLs, or we can do classifications through NBAR. Okay? So classifications through ACLs is, hey, it's in this VLAN. It's part of this network. Well, if I'm using voice VLANs, so one way to do this is voice VLANs. Voice VLANs means the voice traffic from the phone is going into a different VLAN. I could use an ACL for that network and basically say, okay, this network is going to get tagged as EF in the marking, okay, according to that. Or I can use NBAR. NBAR is, I forget their stupid acronym for it, but NBAR is basically a layer 7 deep packet inspection for quality, for QoS. So what NBAR does is it automatically classifies stuff for you based on layer 5, 6, and 7 information. So instead of by IP address, let's say I'm mixing my voice traffic with my data traffic. They're not on separate VLANs. I could use NBAR on a Cisco device, and NBAR is going to go through and detect the voice traffic and classify it as voice traffic. It's going to dig into the packets and the frames and see what's in them and classify it. This is the same thing as an application-aware firewall. So an application-aware firewall does essentially the same thing as NBAR, but it does it for the determination of, am I going to allow traffic back in? Okay. NBAR looks into the traffic, but looks at it to find out what kind of traffic it is so it can classify it. Is it data? Is it video? Is it voice? And NBAR can detect thousands of different kinds of traffic. And it's all in NBAR. So let me see. Let me show you. They have it. Let's see if I can pull it up. It'll give me just a moment here. Yeah, see, I don't have Edge installed, so I can't open the book that I need. Okay, NBAR stands for Network-Based Application Recognition. Okay, right here. So what NBAR is, it's a mechanism for classifying traffic, okay? And it can do that by identifying the application, meaning layers 5, 6, and 7 is what we're dealing with here in the OSI model, okay? There are other ways that we do this in different ways. So an application-aware firewall does essentially the same thing. It identifies applications and looks at their layer 5, layer 6, and 7 stuff to determine if the communication's open and if it should be allowed out of the firewall. When we're talking about deep packet inspection, we're essentially doing the same thing that NBAR does, in that we look deep into the packet into layer 7 to see what the actual data is. NBAR has a bunch of signatures in it that identify what applications. I was talking about Palo Alto. I'd mentioned Palo Alto firewalls, okay? Clark College recently has just recently swapped over to Palo Altos. Palo Altos makes Cisco's look cheap. And the thing that Palo Alto does better than anyone is this, application recognition. So they will write signatures for custom applications. If you submit your application that you have in your company, you submit it to them, within a few months, they will write and send out to everybody the code that identifies your application so that now you can have prioritization and policing and shaping, which we're going to talk about, through that device. So it does full web-based firewall inspection, and it does full shaping and prioritization. okay, when you're talking about a Palo Alto. It's doing very much what NBAR does. Okay, we have many mechanisms of doing this that we do for firewalls, for different things. NBAR is the process that we use in what they use in Cisco. Obviously, Cisco Systems developed NBAR as part of its content networking platform. Just be aware that many companies have this type of feature. This is not an uncommon feature. NBAR, specifically to Cisco, is focused on prioritization of traffic. But we identify applications for firewalls, for all kinds of things, because we do so many different things with the traffic based on the application. Are ACLs really flexible? No. Their IP address, source destination IP, okay? Their ports, source destination ports. NBAR and the other mechanisms that are similar, that are able to identify applications, are on a whole nother level of capabilities compared to what an ACL can do. Because ACLs can only operate at layers 3 and 4. And they do make layer 2 ACLs, by the way, just to clarify. They do make ACLs that work on MAC addresses. We don't use them. We don't use them very often because of the issues with them. We do layer 3 ACLs. So it's rare that most normal admins are ever going to really use layer 2 ACL, right? Okay. So this is an important thing because this is really the next step for how are we classifying NBAR. NBAR is doing our classifications for us. It's doing the identification of the traffic so that we can classify it. And then we're setting the rules for what the marking of those classifications are. This kind of traffic goes into AF12. Okay, that's a queue. We'll explain the queues here when I get into that. I don't think it's in my slides. Whoops. I don't think it's in my slides, but it's in my book, or in the book on the classification stuff. I don't think the slides go into that much detail. Any questions so far on that stuff? So we'll get more into that. So Qos mechanisms. So these are the three. We started to talk a little bit last week about this. We have the best effort model. This is basically there is no quality of service. Okay, that's standard IP is best effort. So we have no quality of service. Then we have integrated services. Integrated services is guaranteed delivery. So you have you don't have a choice. Okay, the data you're dealing with is incredibly important, and you don't have systems in place, or the type of data doesn't have good mechanisms built into it for dealing with quality of service on its own. Okay, you can do integrated services. Our focus is differentiated services. We're not going to spend a lot of time in integrated services. That's much more advanced, and it's not as scalable. The biggest problem with integrated services is that here's the big difference. Integrated services, the things that need the services can request them. That's not how differentiated services works. Devices can't request resources in differentiated services like they can in integrated services. With integrated services, if you have too many devices acting or asking for resources, and you run out of resources, it greatly interferes with the performance of the network. Okay, so there's really some severe limit on scalability. I don't know. I have not personally worked heavily with quality of service, so I don't know of a situation where it would make sense to go with integrated services unless you had to have traffic that was absolutely guaranteed. Okay. Differentiated services gets pretty close. So provides high scalability and flexibility in implementing Qos. Network devices recognize traffic classes and provide different levels of quality of service to different traffic classes. Okay. So what are the benefits? Best effort. So we're looking at the three different models. This model is the most scalable. There's no guaranteed delivery. Scalability is only limited by bandwidth limits, in which case all traffic is equally affected. Packets will arrive whenever they can and in any order possible if they arrive at all. That's a drawback. No special quality of service mechanism required. It is the easiest and quickest model to deploy. Well, best effort is basically just basic normal routing, right? But as I said before, how have we solved quality of service on the internet? Best effort is how we solved it. We solved it by throwing bandwidth on it because we can't implement integrated services or differentiated services on the internet. On a private leased line, so if you had a T1, you had an OC carrier, you got PPP over it, that kind of stuff, a leased line, then you can have quality of service across that leased line. Okay, if the leased line doesn't go to the internet, it goes to another location. That leased line is not on, it's a private business connection. Okay? So here is integrated services. Use resource reservations and admission control mechanisms as building blocks to establish and maintain quality of service. So you reserve resources and then you admit the traffic that's allowed according to those reservations. The edge router performs admission control to ensure that available resources are sufficient in the network. Okay? So we have a quality of service aware node. We have our end-to-end signaling that is happening. And then we have so dynamic resource allocation is going to happen. So when this basically wants to communicate with this, these are going to request resources for this communication. In many ways, this is real similar to circuit switching, isn't it? Isn't that basically what circuit switching is? You dedicate resources to a communication, okay? And of course, the problem with circuit switching is we run out of circuits when we run out of capabilities, right? With packet switching, we can do queuing, we can do buffering, we can do all kinds of techniques to allow for more communications and stuff going on. Where in circuit switching, we really can't. We have a number of circuits that we can physically make, and when those circuits are used up, we can't make anymore. Okay? Think of it that way, where integrated services, you're requesting dedicated, and we only have so much that we can dedicate towards it. And there's a lot of signaling that's going to be happening here. That's going to be some of the overhead involved with integrated services. Okay? So, if network devices along the path can reserve the necessary bandwidth, the originating application can begin transmitting. If the requested reservation fails along the path, the originating application does not send any data. So, if there's no resources, if you can't allocate the resources, you don't get any traffic flow at all. It just doesn't even send it. That's good in some ways. It doesn't saturate the network with traffic, but that means that your application doesn't work. When there's not, again, all circuits are busy. That's exactly what the scenario that you're setting up with this kind of model. I think that is a great way to think of it. It is a circuit switch quality of service model. Is how it operates. Okay? Then differentiated services. Oh, this is so much better. And basically, you mark it with all these different queues, and Diffserv has different things integrated with the way the queues work, right? You can have that voice queue. That voice queue is called EF. We mark it as EF. That one sits above all other queues. And then we have AF queues. There are 4 AF queues, and within each of the 4 queues, there are 3 drop levels. So like AF11 is AFQ1, drop level 1. AF13 is Q1, drop level 3. What it means by the drop level 3 is most likely to be dropped within the queue. Drop level 1 is least likely to be dropped. Okay? So you have AF3 would be AFQ3 with a drop level of 3. AF4-3 is the worst queue of the AF queues that you can do. Okay? So you have basically 4 queues, 1 through 4, and then within each queue you have 3 drop levels that are managed within that queue. So if I say, okay, this is super low priority, it's going in Q4, okay, and it is super low priority within Q4, then it's in group 3. So it's most likely to be dropped when there is issues. Okay? So, specifies a simple and scalable mechanism for classifying and managing network traffic, providing quality of service guarantees on modern IP networks. We basically call it almost guaranteed quality of service, where this is guaranteed reservation of traffic. This is as good as we can get. Eventually, though, with Diffserv, you will lose traffic if you do not have enough bandwidth. Okay? This will just stop the application from running. It won't be able to send traffic, it won't work. You'll get errors and stuff if there's not enough bandwidth available. This will give it a try and let the traffic get dropped in the queues when the queues overfill. Okay? So we use what's called a soft QoS approach. It works on the provisioned Qos model, where the network elements are set up to service multiple classes of traffic, each with varying requirements. Diffserv divides the traffic into the classes based on business requirements. Each of the classes can then be assigned a different level of service. Okay? So here's the deal. Notice that the nodes are unaware of quality of service. So with integrated services, the nodes participate in quality of service and request the resources. Here, the nodes don't know anything about quality of service. We use NBAR or ACLs or other techniques to identify the traffic and classify it. And then once it's classified, we then mark it in different ways, depending on if we're marking it at layer 2 or marking it at layer 3. Okay? So with differentiated services, we're putting them in different classifications. So how do we do this? Avoiding packet loss, drop the TCP segments, cause TCP sessions to reduce their window size. So it's actually congestion avoidance. I'm not quite sure why they've laid it out this way. So here's the tools that we use. Okay, we call it classification and marking. That's the first part. Then we have congestion avoidance. Here's how congestion avoidance works. When TCP, remember about TCP and the window size, flow control in TCP. The TCP flow control works by increasing the window size every time we get a successful transmission. So the window size, maybe it accepts 2 blocks, 2 segments. And so I send 2 segments and then it accepts those. And so it raises the window size to 4 blocks. So I do 4 segments. Then it raises it to 8, and then 16, and then 32, and keeps raising it so long as the traffic keeps going until packet loss occurs. Then the window size starts going down. Well, so what this can do is part of the avoidance. IP does not have built-in congestion avoidance capability. Okay? There's no built-in capability to IP itself. There is in things like frame relay. Frame relay has built-in congestion notification. We call it fecken and beckon. Okay, forward express congestion notification and backwards express congestion notification. And it's how where one router will inform another router, or a frame relay switch will inform another frame relay switch to slow down traffic, right? We don't have anything like that in IP to be able to do that. So they use a trick. If we shrink the TCP window size, we cause it to send more acknowledgments, require more acknowledgments. That slows the TCP connection down, preventing congestion from happening in the first place. Okay? So where we're talking congestion avoidance tools, what we're talking about is modifying TCP as it flows through the device to shrink the window size to artificially cause TCP to slow down without losing traffic and without actually causing congestion, preventing the congestion from happening by using TCP's built-in mechanism of shrinking the window size. Okay? So that's how they do it. Now, editing TCP window size in certain kinds of VPN would trigger an error, would show that the TCP has been altered and would cause the integrity to break. So if we're doing integrity checking and we have a Qos tool editing, it could affect our VPN. That's one of the concerns of using that capability. You alter that TCP in this way, and if you're using SSL that's watching that or something like that, then it's going to detect that it was altered in transit. You're gonna drop your integrity checking. Okay. You had a question. The amount that can be sent before an acknowledgement. So like, if let's say I say 3,000 bytes, I can send 3,000 bytes and then I'll stop until an acknowledgement from the other side is sent. Well, if I keep increasing that window, it increases the speed of my connection. So instead of, and it will automatically shrink window sizes on its own when the information drops. What we're trying to do is never get to that point by shrinking the window size artificially earlier on in the congestion process so our queues don't fill up. So TCP doesn't have to automatically do that. We can trick it before it happens. We want to slow connections down before we actually lose traffic. If TCP is doing it on its own, adjusting the window size, it's because it's already losing traffic. That's what will trigger TCP to shrink the window size, is a missing acknowledgement, meaning data wasn't sent. So that's how we're tricking it. So traffic classes are allotted a portion of the network resources as defined by the policy. Okay. So that's part of it, is we do that, but we also do the TCP intercepts. The quality of service policy also identifies how some traffic may be selectively dropped, delayed, or remarked to avoid congestion. So I'll talk a little bit more about that. The primary congestion avoidance tool is WRED and is used to regulate TCP data traffic in a bandwidth efficient manner before tail drops caused by queue overflow happens. Okay, what's a tail drop? What's a tail drop? They show it really well in the book. So you have your queues, right? You have your queues, and your queues begin to fill up. Tail drop. These drop out of the queue because there's no room in the queue. So these are new packets coming in that have not been waiting in a queue, and the queue is full. Tail drop happens. So these are getting dropped before they're even waiting through the queuing process and timing out. Okay, we want to prevent this from happening. This means our queues are getting too full, and one of the things is we want to prevent tail drop from happening. How we are going to do that is congestion control. We're going to try and slow down the connections so our queues don't fill up. This is the lowest priority queue, so all of these are going to start dropping off and never making it into the queue because the queue is full. So it's just going to discard the traffic when it hits the queue. Okay, this is called tail drop. So why we're doing the congestion notification is to prevent tail drop from happening as much as possible. If you're getting an enormous amount of tail drop, it may be that you just don't have the bandwidth for what you're doing. It's not going to solve it if you're oversubscribed too heavily. It's not like quality of service is not that magic wand you wave over and, hey, I have more bandwidth. That's not how this works. It's okay, I have sensitive stuff I need to treat a certain way, and so I'm going to treat it that way. I may have plenty of bandwidth, but I'm still going to maybe classify my voice traffic and stuff. So in case there's ever a bandwidth constraint, it's handled. But if you're running where the majority of your time you're in queues and your queue depth is high, and that's just a normal operation of your network, then you are out of bandwidth. You need to upgrade. You have to add bandwidth to it to solve this problem. Your quality of service is only going to extend so far. And even with lots of bandwidth, as I said before, usually we can just throw bandwidth at it, okay? But there are plenty of reasons to still want to prioritize voice traffic when you have plenty of bandwidth to keep jitter to a bare minimum, right? So prioritizing traffic is going to keep jitter even when you don't have much of a bandwidth constraint, okay? Meaning your queues are pretty much going to be empty all the time. But you don't operate on first in, first out. Voice, when voice arrives, it goes, and then everything else has to wait if it needs to. And so there's times where you'd want to do that. Okay. Congestion management. This is where traffic exceeds available network resources. Traffic is queued to await available resources. Common Cisco iOS-based congestion management tools include class-based weighted fair queue, low latency queuing. Okay, these are the queuing methods we already talked about. That's the congestion management tools are the queuing methods that we have. We're going to also talk about policing. Okay, so what about marking? How do we mark something? So we've talked about the queues. So that's how we manage it once we've classified stuff, and once congestion occurs, we manage it by doing queues and assigning priorities to those queues. And if the queues get too full, some of that traffic gets discarded or dropped. And the prioritized traffic goes. Now, if this is TCP traffic, TCP is going to recover from that, slow things down, and you're still going to get your traffic, but it's going to slow your connection down as we want it to. Okay? So these are the different ways that we can mark. So there's more than one, and these all don't necessarily talk to each other. Okay? Before a packet can have a quality of service policy applied, the packet has to be classified. Methods of classifying traffic flow, you can do layer 2, layer 3. We can do ACLs. We can do class maps. We can do all kinds of different ways. We can use NBAR as the way that we classify. There's all kinds of different ways that we classify the traffic, okay? That we don't need to get too much into. Just know that ACLs is a big one and NBAR being the other big one that we use. So at layer 2, we can do Ethernet. So it's Ethernet, and notice it's part of 802.1q. Okay? This means that it's part of the .1q standard. This one here only works on trunk links. Okay? So this is actually in remember, if you remember the tag, there's a couple bits in the tag for prioritization. Okay? For a class, and when we're talking the .1q tag that goes into a frame for VLANs, the VLAN tag. Okay? That VLAN tag only exists when the frame goes over a trunk. Okay? So this here only works on a switch when it's going over a trunk. That's what this particular, so it's a layer 2. It's called class of service, but it's tied to the 802.1q tag. They make that pretty clear in the book when you read that section. Then we have the TID, the traffic identifier. This goes for Wi-Fi. So that's our prioritization in Wi-Fi that we use. In MPLS, it's a layer 2, and we use what's called experimental, and it's 3 bits. So that's how we mark it in MPLS. In IPv4 and IPv6, we have 2 methods. We have IP precedence, which is an older method. It's a layer 3, okay, and it's called IPP, and it's 3 bits in length. And then we have Diffserv, DSCP, Differentiated Services Code Point, DSCP, okay? This is what we are mostly talking about as Diffserv. This is what we use the most today. And DSCP is backwards compatible to IPP. All the code numbers for IPP are available in differentiated services. So there's backward compatibility between these two. But basically, we've got to mark the traffic, so we classify it. We've got to somehow mark it. So these are the different methods we can mark traffic. Here's an example, marking at layer 2. So here we have an Ethernet frame, our preamble, our start frame delimiter, our, so here's our VLAN, right? So we're going to put in our tag right between the source address type length field. We're going to put in our VLAN tag, okay? We got 2 bytes of the VLAN tag, and these 3 bits here is for the COS priority, okay? So that's where we're going to insert that. Now, marking at layer 3, we're going to put it into the type of service header or type of class. If we're doing IPv6, it's type of service in IPv4. And we have 6 bits and then ECN is congestion notification, those 2 bits. Okay. Okay, so we talked about trust boundaries. Already talked about those. Traffic should be classified and marked as close to its source as technically and administrative feasible, meaning the phone or the switch, but it's got to be something that we control. Congestion avoidance, when the queue is below the minimum threshold, there are no drops. As the queue fills up, the maximum threshold, a small percentage of packets are dropped. When the maximum threshold is passed, all packets are dropped. Okay, shaping and policing. Here's the difference. Shaping and policing. Policing, you can do 2 different things in policing. Policing, you can drop the traffic that goes above the rate limit. Okay, so when we're doing shaping and policing, it's rate limited. I have a gig connection, right? I have a gig Ethernet connection hooked into my router, but my actual bandwidth that I pay for from the ISP is 200 megabits. So my committed information rate, the amount of traffic they'll guarantee to cover to transmit for me, is only 200 megabit, but because it's plugged into a gigabit Ethernet port, it's a gigabit connection. Okay? So I would set up policing to drop all traffic that goes over 200 megabit. Okay? That would be one way I could use policing. It would just drop any traffic over that 200 meg limit, because if I send that traffic over my WAN link, I'm not guaranteed that it's going to be there, that it's actually going to go, because I'm only actually paying for 200 megabit, even though it's negotiated as a 1 gig link. That's the drawback of Ethernet. Okay? So I may want to do policing to do that. Now, the other thing I can do in policing is I can alter the traffic. So for instance, after it hits the 200 megabits, I could alter the traffic to say that it's discard eligible. So any traffic over 200 megabits is marked as discard eligible. So it won't automatically get discarded, but if there's congestion, it will be discarded by the ISP. Okay, so that's one way I could do that. Or I can do traffic shaping. Traffic shaping is just like policing, but we don't drop the traffic, we slow it down. Okay, so shaping is we queue up, we buffer the traffic. Okay, so I have 200 megabits and I've set shaping in. I'm going to delay traffic to stay under the 200 megabit bandwidth that I've paid for. Okay, so the traffic's not going to be dropped necessarily, but it will be delayed. Now, if it's delayed too much, as in again, I'm sending too much compared to the bandwidth I have, traffic will drop simply because it times out. Okay, the TCP timers and stuff like that expire. So, policing, I can either drop it or remark my traffic. So I can change the marking of it to have that traffic treated differently. Okay, when it reaches over a certain limit. Or shaping, I queue the traffic. Okay, and I delay the traffic to keep it under a certain rate. Always keep in mind with shaping and policing, we're talking about rates. So I could say I want to shape web traffic so that web traffic is never more than 150 megabits of my total traffic of my bandwidth. Let's say I have a 200 megabit link, but I never want port 80 or port 443. I don't want web traffic to ever exceed 175 megabits of that bandwidth. So I could set a shaping policy that anytime web traffic reaches that limit, that it then starts shaping it and queuing it and slowing it down. So it does not exceed 175 megabit. Okay? That's how I would use policing. Or excuse me, how I would use shaping. So we do traffic shaping all the time within companies to give voice a certain amount of guaranteed bandwidth. I can actually say, hey, I'm going to shape everything so that there's leftover bandwidth, specifically for voice. Okay. In addition to the queuing, in addition to the DSCP stuff, we can do shaping on top of that. So traffic shaping retains excess packets in a queue and then schedules the excess for later transmission over increments of time. Policing is applied to an inbound traffic on an interface. When the traffic rate reaches the configured maximum rate, traffic is dropped or remarked. Okay, that's what they have for it. Now, I got to say the book definitely does a better job covering some of the things. Just keep in mind, you've got the queues that they discuss in the book. Is EF and AF. Okay? EF is one queue with no drop priorities. EF is where voice automatically falls into. Okay, when you're using NBAR is gonna mark all your voice with EF. That's how it's gonna be configured. AF is where we have the 4 queues, so most of your stuff is gonna go in AF queues. Okay, and you have AF 1, 2, 3, 4. Okay, this being the highest priority, this being the lowest priority. And within each queue, you have different drop rates. And there are 3 drop rates. Okay, so if I put a certain traffic and I choose to mark it, I classified it, and I'm going to classify it as AF22. That means it's AF, it's in Q2, and it's drop rate 2. That means when the things within this queue are competing, a 3 and a 2 will be dropped over a 1. Okay, so this one here is the most likely to drop within this queue, and then, so most likely, and then the next one, this is less likely because it's a higher priority queue, and within that queue you have your drops. And so how we call it, we say, okay, that traffic is in AF23. So it's AFQ2 drop rate 3. Okay, so that's how the queues go. So you just have one normal big queue, that's all your voice stuff. This is basically everything else. So this is what NBAR, this is what the commands are doing when you're classifying the traffic. You're saying, oh, it matches a certain ACL, classify that matches a certain ACL as one of these queues. That's what gets marked into the frames and the packets. Then when the routers receive that and there's congestion, they apply whatever the queuing that is configured on the router to be able to do. Okay. Any questions on quality of service? It's complicated. It gets more complicated. This is it, though. This is all you really need to know. Not too bad there. They do a good job going on into it in the book, but I think they actually, I think they go maybe a little bit too much. Definitely, there's some stuff in there that you probably don't need to know. Okay. Talked about DSLAMs. We've talked about broadband connections. Before we continue on, do any of you have questions about home or small business connections at all? Anything related to, how they work, what they are, what's available? Because we've talked about, so do you understand how home users get connected, how this stuff works? what components are we talking about. So like when we're talking about a home user who's working remotely at their house, they're oftentimes going to be on like a company provided laptop, but not always. Sometimes they're on their own home computer. And so that changes the dynamic of what we can control, right? If they're on a laptop, then I can actually control it with Active Directory and install software on it and stuff and manage it, right? Versus, well, and think about the technologies that I'm going to need to be able to do that versus someone who has a home computer, right? How am I going to address teleworkers who I do not issue laptops with? Well, make it so there's no software that they essentially have to install, very little to no software to install. So everything is cloud-based and it's all through a browser. Okay? That's a different style of VPN than if I were to provide a laptop and it be software that's installed on the laptop. The style of connectivity of the equipment I need to be able to facilitate that differs. Okay? So for teleworkers, we have to, and the teleworkers are more and more all the time, and you're going to have some stuff that is cloud-based, and you're going to have some stuff that has to be installed, and you may issue devices. So you may have to manage those devices remotely. How the people connect to your company is important. If it's their home computer and you're cloud-based, then you theoretically, they could work from anywhere. They don't necessarily have to be at home if it's all cloud-based. So what kind of connection they have doesn't matter so much. Also, doesn't matter that we need to support a certain style of VPN. Okay? So VPNs have some drawbacks and bonuses, and some of the drawbacks is not all VPNs are created equal as far as security, and they're not all as useful for different things. So a site-to-site VPN would make more sense, or even a remote access IPsec VPN would make more sense for a person that is using a company device. Okay? They're using a device that was issued to them by whatever company they work for at home. Okay. Now, if we're using someone where they're using their own computer, it would make much more sense to do an SSL, basically a TLS-based VPN, which is like when we go to the bank, right? When you go to the banking website, it's all encrypted. That's TLS. That's a TLS VPN, or it used to be called SSL, right? Secure Socket Layer. Okay, so let's do, we'll come back to Pppoe, that's one of the ways, but let's talk about VPNs first. Okay. So, what if we need a secure connection and for whatever reason a VPN's not an option? Then we'd have to get like a leased line or a business connection to a person's home if we had home workers. Right? So VPN is how we take care of this today. Okay, and there's a wide variety of VPNs. There's quite a few different styles. Just a flavor. Okay, we'll talk about all the different flavors here. So I'm going to go much more into the book's got more. We go more into than what the slides have. So for VPNs, first off, we have two basic flavors. We have site-to-site and remote access. That's the first thing to get clear is the two different types. Site-to-site is transparent to the end devices. They don't know they're on a VPN. A site-to-site is between two routers or two servers, okay? It is at the edges of the network. So if I had a site-to-site at home, I would have a router that has site-to-site VPN capability. And it would be pre-configured to run a site-to-site VPN to the company I work for. And then any device on my network can connect over that, and there's no special configuration or anything involved. It just knows if it's traffic that's destined for my company's network, then it goes over the VPN, and if it's not, it goes out to the internet and doesn't go in the tunnel. That is a site-to-site. Site-to-sites are great when you need to connect many people or several people at one location to your remote site, right? You have a branch and there's 4 or 5 people there. We do a site-to-site VPN in that instance. You're just going to get them a normal business internet connection and then run site-to-site over that. The other way is remote access. Remote access is like, for instance, you go to your banking website. That's a remote access VPN. You have a client. In this case, the client is the browser. Okay, and that's actually what we call a clientless SSL connection. Okay, it's what we use. Everybody uses it every day that they go on the web. It's the norm. Okay, it's the clientless SSL connection. Okay, that is an example of remote access. A client software to a device. And you know you're connected securely because it has the big icon that tells you you're connected securely. Okay? It is obvious to the end user that a VPN is in use when you're doing remote access. It's obvious to the computer involved because the computer has to have software installed on it. Your phone has to have a VPN client installed on it. Okay? And so there's clients that we have to install for remote access. Remote access is what we use when it's just one person connecting. Okay? They're on the move. There's only one person at their location. These are salespeople. These are all our people that have to be on the move or that work from home, and it's a dedicated device. It's their home computer, and we've had them install some software for the client to form the SSL. Okay, to form a VPN. And there's a couple different versions of VPN that we can use. One of the other things I want to get into first, that before we go into the different types, is what is the two flavors of encryption. So let's do a little cryptography first. We'll take a break here once I finish the cryptography. We have asymmetrical and symmetrical encryption. Which one's which? What does it mean? What is symmetrical encryption? Anybody know? Same. Same what, though? Same key. Okay? So, the same key in symmetrical encryption, we use the same key to encrypt as we do to decrypt. The benefits. Fast. It is very, very quick. It can handle large amounts of data in this way, and the math is simple. The key size can be much smaller, okay? Because of not as much complexity, because the same password is used to encrypt as to decrypt, it's faster. So most technologies that we use in VPN oftentimes are going to use some form of symmetrical encryption during the VPN session. So while I'm transmitting data back and forth across the VM, while that streaming data is there, I'm using symmetrical encryption. We're typically using AES. So today, like some of the examples of symmetrical encryption would be DES, 3DES, and AES. Today, what we use is AES. Okay. DES and 3DES are ones that we don't like to use anymore. DES especially is broken, but the strength of the keys, their key space is not as good. AES has a very strong key space, and at 256 AES, we have yet to break it. I don't think they've broken 128 AES yet. Okay. It's one of the strongest encryption algorithms that we have that is not quantum. And supposedly AES 256 is supposed to handle quantum breakage. How legit is that? I don't know. But AES is basically the go-to symmetrical. Okay. Then we have. So for instance, you're encrypting a file on your hard drive, symmetrical. Okay. You're encrypting your entire hard drive, symmetrical. The same key is used to encrypt as to decrypt. Okay, asymmetrical. Okay, this is RSA. And we also refer to it as PKI, public key infrastructure. Public key, private key is another way that we call this. Okay, RSA is one of the algorithms. We use, RC4. So RSA Rc4 is what we're using now. Rc4 we're trying to get rid of, I think. If I recall, one of the complaints about Rc4, I think it's Rc4, don't quote me on this, but the NSA had some of their people on the board that came up with this. And so they're concerned of NSA's involvement in the security of Rc4. Rc4 used to be what protected all the websites for banking and everything. That's what SSL used to use. I think they're swapping it out. I'd have to do some more investigation to get the details of that. But I've seen several articles that were talking about bad things Rc4. I just don't remember the specifics. Okay. So what is asymmetrical? A different key is used to encrypt than to decrypt. This is how we do digital signatures. Okay. So you have a public key and a private key. Here's how it works. If I give you my public key and I write a message and I sign it with my private key, when you open it, the public key will verify that it was signed by me, because only something signed with my private key can be opened with the public key. I encrypted with the private key. You can then open it with the public key. If it wasn't done with my private key, you wouldn't be able to open it. So it guarantees that I am who I say I am. Okay? It means only the person who had that private key, meaning if you lose your private key, this all goes out the window. This is why private keys are gold in a PKI, a public key infrastructure. Okay? Who holds the private keys? VeriSign. Okay? Those companies that do digital certificates, they have private keys that they sign, and you give a public key. They're the one, that's how they verify. When someone reads your public, reads that was something signed by VeriSign, they know it's legit. And the public keys are just available out there. They're in the browsers. There's about 80 registrars that we accept their public keys from. And so their public keys are into the browser. Right now, Symantec is about to lose theirs. I think it's Symantec. Chrome is about to pull their keys out, so anything signed by them will no longer be valid in a browser. Chrome will give an error saying it's unsecured. It's not a trusted certificate. Okay, this gets into certificate authorities and all kinds of crazy crap. But the benefit being is we use it for identification. So when you build a VPN tunnel, we use asymmetrical encryption to do the setup, to do the authentication, right? We'll have digital certificates, smart cards. That's what they are. Smart card, you plug it into a slot, it's got a digital certificate on it. And that's how it's identifying you. So asymmetrical encryption is mainly used to establish connections and to identify hosts, to identify the people. And then a symmetrical tunnel is built using that information. So identify, and then I build the symmetrical tunnel, and everything goes through the symmetrical tunnel. Here's the reasoning for it. The processing needed for asymmetrical encryption is much, much higher than symmetrical encryption. So the bulk of the encryption you want that's actually doing it in real time and doing a lot of data, we want it symmetrical in almost all instances that we can. But how do we then protect the key? So we have these mechanisms in VPNs where we can generate symmetrical keys using an asymmetrical algorithm. The asymmetrical one we like to use is called Diffie-Hellman. DH. The Diffie-Hellman algorithm is used to generate a symmetrical key for a VPN over an asymmetrical tunnel without sending the password. It uses logarithmic math to generate a password that's never actually transmitted. That's how it generates a key. And it's not just like a typed password. It'll be a ridiculous key. And what version of Diffie-Hellman determines how big the key is. That's really important. Because if you don't use the right version of Diffie-Hellman, you'll have a weak VPN. You'll have a weak key for your AES. Okay, so one of the hallmarks of VPN is IPsec. Okay, what are the two main types of VPN we use today are SSL/TLS. Okay, secure socket layer is old and dead. We use the name, but we do not want to use SSL anymore. Most versions of SSL are banned. SSL 3.0, most of the browsers and most of the servers are dropping support for SSL 3.0. That was the last version of SSL that came out. This is highly insecure. We still use the name SSL all the time, but usually we're actually talking about TLS. Okay, and today we want to use TLS 1.2 or higher, not 1.0. TLS is transport layer security. This is how we protect the web. This is a remote access VPN technology, usually. Okay, here's a trick. You have one server pretend to be a client, and the other server pretend to be the server. You can make a site-to-site VPN that way. So we use, even though SSL and TLS is remote access only, we've tricked it, and we'll use it as site-to-site. So we'll do that. Okay. Why would you use this over IPsec? This works through firewalls and works through NAT. This works at layer 4 and 5. This works at a higher layer. Where IPsec works at layer 3, NAT will screw up IPsec. Okay? So this is why we use SSL and TLS. It's not as secure, but it works from anywhere. So when you have someone it's browser-based, clientless, we're doing this. Okay? When we're using a browser for our VPN technology, for banking, for whatever, we're doing this. And in fact, in a Cisco ASA, you can set it up where you go to a web page, you sign in with your credentials, and you can access applications, and it's all through a web page. So any usable browser, any good browser works. That's the future. That's what we're doing now and want to continue to do because it's so much more flexible. The phones, you can do it from any device, and we just make all our applications web-based, hence SQL and PHP. Everything's going to be SQL and PHP driven, more so now, having more and more every day. Okay? So TLS is what we're using to secure that technology. That's the type. And we're using a remote access VPN, and the VPN is going from your web browser to the server. And the server is chunking on the TLS stuff, and so it does add some extra overhead. When you run a secure server that runs on port 443, that's HTTPS, that HTTPS means you can accept less users hitting that one server at a time because of the processing. You got to process asymmetrical encryption. Okay, you have to use certificates in the browser that are trusted to build the tunnel. And then it builds usually a symmetrical tunnel to do that with. Okay, using the certificates to make sure who's talking is exactly who they're supposed to be. Then there's IPsec. IPsec's my favorite. It's the most widely used besides this, and it's IP security, IPsec. It is a standard, and this thing, these are somewhat flexible, but this is crazy flexible in what you can do. It's a 5-tier framework. Okay, so you have here, I'll bring it up on the screen instead of drawing it all up, so that way it's saved as well, so you can see this. Okay, so we'll cover this slide here in just a second. Now, we should need to take a break too. So IPsec and IPsec we use for IPv6 as well. So this is a picture of what the framework looks like. Okay. And so the IPsec, so SSL and TLS isn't as configurable and as extensible as this is. The cool thing about IPsec is this framework can remain the same while adding new algorithms and new protocols to it. It's a collection of capabilities, and you pick and choose the capabilities you want for a particular tunnel. You can use IPsec as either site-to-site or remote access. It does both, okay? And so first we have IPsec. We have the actual IPsec protocol, and this is Authenticated Header and ESP. Authenticated Header is exactly what it sounds like. It authenticates and provides integrity checking for just the headers, not the payload. This is encapsulating security payload. This will encrypt the payload of the IP packet. You can combine both of them, and then you get protection against the entire packet and its contents. So based on, hey, I don't need encryption, I just need integrity checking and authentication. Then I do authenticated header. Oh, I'm not worried about the headers because the headers are going within my network. I only need the payload encrypted. I'm not worried about headers being altered. I'm going to do just ESP, or it's going over the internet. Well, I'm going to do both. Okay. Then we have confidentiality. What algorithm are we going to use? AES is usually what we're going to use. These are the ones that are currently supported: Seal, AES, 3DES, DES. AES is what we use in modern today. Then we have integrity checking. Integrity checking, we run a math algorithm, right? It generates a hash. We go to the other side. We do it again. If the hashes match, then we know it hasn't been altered in transit, okay? And so we can do MD5 and SHA. MD5 is the older one. SHA is the new one. SHA-1 we don't use. We're now on SHA-2 or SHA-3, I think. Then we have authentication. PSK stands for pre-shared key. For RSA, you can do what are called RSA nonces. Don't worry about that. And RSA certificates, okay? So when forming an IPsec tunnel, I can use just a pre-shared key, or I can use RSA certificates to be able to identify, which means I can identify the hardware with an RSA certificate. So I can do not only authenticate the hardware, I can authenticate the user with certificates. And then Diffie-Hellman is the algorithm we use to generate the key that goes into the symmetrical tunnel. So this starts out as an asymmetrical communication, and it builds a symmetrical tunnel. We have what's called a phase 1 and a phase 2. The phase 1 tunnel is asymmetrical, and it's used, and then Diffie-Hellman runs. Diffie-Hellman is an asymmetrical algorithm used to generate symmetrical keys across a secured link, okay? Or actually across an unsecured link. So what we do is we form a phase 1 tunnel, and then the phase 1 tunnel negotiates all the parameters for the phase 2 tunnel. The phase 2 tunnel is a symmetrical tunnel that all the traffic goes in. That's how IPsec works. And I can kind of pick and choose based on the performance I want and the level of security. I can pick and choose these items to build, and so long as it's configured the same way on both sides, I can get my tunnel to work, okay? Where SSL is not as extensible as this. TLS, SSL is not as extensible. What are we using TLS, SSL for today? HTTPS. We're really using TLS, okay? So SSL versus TLS. And we can do a quick search here. What's the difference? Okay? Transport layer security and SSL are protocols that provide data encryption and authentication between applications and servers in scenarios where data is being sent across an insecure network. Okay, the term SSL and TLS are often used interchangeably. That's what you got to get across, is they're often used interchangeably or in conjunction with each other, but one is in fact the predecessor of the other. SSL 3.0 served as the basis of TLS 1.0, which as a result is sometimes referred to as SSL 3.1. With this said, though, is there actually a practical difference between the two? Okay. So how are they different? Port-based protocol. That's more than we need to get into, so I'm not going to go any further than that. But it's maybe something interesting that you want to look into. Pre-shared key. versus RSA. RSA is dudes' names. It's the three guys who made it. Rivest is the R. So RSA. It's Rivest, Shamir, and Edelman. That's who developed RSA. And RSA is the basis of public key crypto that we use today. So the other thing we do, the other thing to keep in mind, so the asymmetrical keys, so a 512 asymmetrical key is broken. We don't use them. A human can factor it, okay? Without a computer, a human can factor a 512. It's been done. A mathematician factored out the signature for the owner of Google, for Sergey Brin, and sent him an email to himself, signed by himself, to prove that Google needed to update all their signatures. This happened a couple years ago, and immediately Google updated. Everybody went, okay, this mathematician dude just factored out a 512K key on his own. That means anybody who actually knows what they're doing with any kind of computer can factor a 512 in no time. And people were still signing their digital signatures for all their emails and stuff like that were still 512 keys that are forgeable. So we had to update it. Well, the highest key we have in symmetrical for AES is 256. Okay? That's the strongest key we have. We either run 128 or 256 in AES. With asymmetrical encryption, a key of 512 is garbage. A key of 1024 is breakable. A key of 2048 is what we tell people to use today. Pretty soon, we'll be telling people to use a 4096 key. That key is huge. That's how many bits are in the key space, right? That is an enormous amount of number of keys. There's only 256 bits in a symmetrical key for AES. You're talking 4,096 bits for an asymmetrical key. And that 496 is not as strong as a 256 symmetrical. Okay? So that's why it's great for certain things, but it's not as strong as symmetrical encryption. But symmetrical encryption requires you give the password away. So there's a trade-off. We use them for different things. Symmetrical makes much more sense to encrypt traffic with symmetrical, where asymmetrical makes a lot more sense to identify people, to identify devices, and that's how we use it. Okay, but keep in mind, key size-wise, they're not comparable. 1024 symmetrical key is stronger than anything we have ever had in asymmetrical. We don't even use 1024. We don't use a 512 key in symmetrical right now. We're using 256 keys. Okay? Go ahead and take a break. Go ahead and take a break. We're going to have a lot of lab time today. A lot of lab time. Okay? The only last thing that we really have to talk about after what I'm covering today is IoT and SDN, and I plan on doing that first thing tomorrow. I'm not going to do it today. So hopefully have about 2.5 hours of labs. Oh my God. Sweet. Dwight is getting my Security Plus paid for. My boss at Clark College. I don't need the Security Plus. I've asked him to get a voucher, and he goes, you know, another route is we can just get it paid for you. I was like, okay, do that. Sweet. Sweet. I'll let her know that Let's tackle them tomorrow. It'll take a little bit. We'll get back. So the issue with Diffie-Hellman is, and this is something that a lot of people don't know unless they do some digging, is that there are many different Diffie-Hellman groups, and they use, one of the groups switches over from one type to elliptical curve. An elliptical curve evidently is better, okay, for the kind of algorithm that they use. And so the problem is if you use Diffie-Hellman like group 2 or group 3, and you use AES 256, Diffie-Hellman cannot create a secure 256K key. It's too big. So Diffie-Hellman makes a really bad key, and it makes your tunnel breakable. So you have to match the version of Diffie-Hellman you use with the key strength of whatever protocol you're using for your encryption in the tunnel. So if you're using AES 128, you can get away with like Diffie-Hellman group 2 or 3 or something. But if you need, you got to use like Diffie-Hellman group 10 or something like that if you're using AES 256 or higher. And if you use way higher in Diffie-Hellman than you need, you're just adding complexity and extra overhead for no reason. Because the higher the Diffie-Hellman group, the more it takes processing-wise to run that process. And that key changes. One of the things we set in IPsec is how often the key rotates, because we want to change the key consistently. We want to consistently change it at random intervals, okay? So within, like every hour, within a few minutes of that hour, we may want to do it. It's depending on whatever you set the settings for. And what that is, that's the window of time that brute forcing is active. So someone could brute force your key in that window of time, okay? So if you set it for an hour, every hour Diffie-Hellman's going to run again and generate a new set of keys to use for the symmetrical tunnel to keep that tunnel running. And now, if someone had copied traffic and tried to brute force it, they'd only be able to brute force an hour worth of traffic before they'd have to guess a new key, right? So you could brute force it offline, but you can't brute force it online because the key is changing too rapidly. Because to brute force a key like this could take months with good equipment. It could take months or years depending on the key. And what weakens it is if I use a weak Diffie-Hellman key, then it could generate a weak AES key. Within each key space, there are known keys that are bad. And the algorithms know which keys are bad and try to never use them. Right? Well, you got to line everything up, all your ducks in a row for it to do all that correctly. Okay, if you get any one of those components in that framework, if any of those isn't matched up properly, then you're not going to get the level of security you think you are. It's either going to be so much load that it's not efficient to use, or it's not secure enough. One or the other is what you're going to end up having. Yeah, Diffie-Hellman, and usually for Diffie-Hellman, like if you get into cryptography, you've got to learn how Diffie-Hellman really works. But pretty much all you need to know is what version of Diffie-Hellman to set, how the commands for it are. And the commands are super simple when you're doing IPsec. You guys aren't required to learn IPsec and command line. So IPsec and command line is what we do in CCNA security. You'll learn how to do all the VPNs in command line and stuff. And they're not bad. I mean, they're a little difficult. I think the firewalls are personally worse. Remote access VPNs are harder to configure than site-to-site. Site-to-site's a lot easier. Remote access, you have all kinds of crap you have to set up because of user accounts and permissions, what they can and can't do across the link, all that stuff. Site-to-site's really simple. You just set an ACL. Says this is traffic that goes in the tunnel. Everything else that doesn't match the ACL doesn't go in the tunnel. So it's pretty straightforward. Well, so D-Wave has come out with a new quantum computer. They're coming out with another one now. They have a new way of doing them, supposedly. I saw that posted, I don't know, a week or two ago. Quantum computers will never replace traditional computers because quantum computers don't work like normal computers. They're meant for very specific things, right? And the reason for it is quantum computers don't get the answer right. When you feed in 1 plus 1 into a quantum computer, you're not going to get 2 is the answer. That's not what quantum computers do. They don't do simple basic logic like that. That's Yeah, see, full time and stuff during that time period. So I think I was dropping the RF signal. Now it's nice and strong. So it's a good chance that he's only getting partial recording. So hopefully tomorrow it'll record the rest. Now I got a strong RF signal. It's always something, man. I try the best I can with this stuff. All right, so we talked quite a bit about VPN, about some of the stuff here. This is definitely more than, some of it is more than what they have in the book, but they do a pretty good job in the book addressing all this stuff as well. So benefits. Why do we want to do a VPN? Well, we don't need that leased line. If you're doing leased line, if you have a nice, T1 and you got no C carrier and you got a PPP over that, you're not using VPN, you have a leased line. Leased lines and even shared connections, if they're not internet connections, don't use VPN. The only purpose for us as end users and for us as administrators to use VPN is over the internet. Okay? Service providers do use VPN for metro, for the metro Ethernet. Like they have to do some stuff. So cost savings. Internet access is vastly, vastly cheaper than leased line. Considering a home user can get internet access for $50 a month, and it's pretty good. You get high-speed internet access for $50 a month. $50 to $80 a month will give you very good access, pretty much in any major city, anywhere in the country. Okay, so the cost is exceptional in savings for the VPN, and that's the main reason we do it, is because every other way is very expensive to do the same kind of thing. Scalability. I can have thousands of VPN tunnels connected to one appliance at a time. I can get a Cisco ASA and have it work as a VPN concentrator. They'll support 20,000 tunnels. 20,000 individual people or sites, locations connected at a time. Okay, and you can get devices that'll even support more than that. So if you're running a huge, like you're running support.com and 90% of your workforce works from home. Okay, that's an example, a good example. Huge amount, a huge amount of their workforce works from home. VPN is their bread and butter. That's how everything works. It's all, everybody connects to a VPN, and then all the software is accessible through web pages and stuff like that, okay? So compatibility with broadband technology. If you can connect to the internet, you can use VPN. VPN will work over dial-up. I'm not quite sure why you would do a VPN over dial-up. It wouldn't be very fast, but VPN will work over just about any kind of internet connection. Now, not all flavors of VPN work over any kind of internet connection, but some flavor of VPN will work over almost any kind of connection you can have connected to the internet, whether that be broadband, wireless, EVDO, WiMAX, whatever you've got. If you've got a solid, stable internet connection, we can push some type of VPN across it. When we have certain things in place, like the microphone sitting on the floor. That's what happened last time, too. Like halfway through, we realized the microphone was on the floor the whole time. So I was walking around, I didn't even notice. This way, at least I caught this one earlier. So it's compatible with just about everything, right? It's going to be like, for the first hour, I didn't hear anything. And then, you guys didn't do anything for like 35 minutes. And then I heard voices randomly and muffled, like you were stepping on me. Well, yeah, I was. Sorry. Yeah, he's going to be listening to us talk about him. You should have been here. Okay. Security. Now, can we make VPNs and tunnels that do not have security? Yes. Not all VPNs are secure. The term stands for virtual private networking. Okay? It does not stand for virtual encrypted secured private networking. Okay? It stands for virtual private networking. So some of the networking is just encapsulation. I stuff it in an envelope. Well, what's stopping someone from opening the envelope and looking? Well, nothing. No integrity checking. No security. Okay? GRE. We're going to look at GRE. It's one of those. It's a transport. I want to hide it in an envelope so I can send it over the internet, but I don't want any of the extra overhead. I just want to hide it. I just do the encapsulation. Okay? Or I want to hide it, GRE, okay, IPsec over GRE. So GRE is the tunnel, IPsec is the encryption and the authentication and everything. So we can add different types of tunneling on top of each other. I can make an L2TP tunnel, a layer 2 tunnel protocol, L2TP, and I can run IPsec over that. So we build the tunnel, and then inside the tunnel, I encrypt the stuff. GRE, okay, IPsec over GRE. I can make the GRE tunnel, generic routing encapsulation, and then I can make IPsec inside of it. Okay, so there's a lot of flexibility, and that's why we have that framework. We can mix and match. You can get exactly the level of security needed in VPNs. An ASA, a Cisco ASA is a security appliance. Okay, it's just like a router. It's just it has routing capabilities. It uses a different operating system than what we know. It's not that hard to learn. When you do CCNA security, you start learning part of it. And what they look like, what they do is they're built for firewall. So a Cisco ASA is a firewall. Okay. And so it's just a dedicated firewall appliance. And what they look like, this is the home one that I used to run. It's about $400 or so. And it does all kinds of stuff, but they get up to really big boys. All right, these are some of the home devices. This is the newest one, the ASA 5505X. Or I think it's 6505, right? No, 5506. Because you have the 5505, that's the other one. This is the 5506. Awesome device. This thing is really, really impressive. It has 2 PoE ports for phones. So like you can run an Office, this can run NAT, run VPN, site-to-site VPN. this would be perfect for like a remote site that's got 4 or 5, 6 people. It can run all their firewall, all their VPN, all their internet access, everything from this device. And power their 2 VoIP phones and handle all the phone calling and stuff like that through it. Okay. Granted, this is about $800, and then a few thousand if you get all the software and capabilities for it. The base price is pretty cheap, but once you add all the features, they get pretty expensive. So these devices have hardcore firewalls, IPS, intrusion prevention systems. They support VPN. They also support content filtering and URL filtering, stuff like that. And these are edge security appliances that you would use. Okay? So oftentimes, now, can we use a normal router to terminate a VPN? Yeah. In fact, many home routers support VPN now. Your more expensive home routers will support VPN tunnels built into them. I have a router that doesn't support VPN, but I could install third-party software on my router. My router supports DWRT or whatever it is. It's an open source routing package that has VPN. And so you essentially get rid of the firmware that your router came with, and you install a third-party firmware, and allows you all kinds of features, but it's open source, it's not perfect. Some things don't work great, but it gives you some things that your normal router, and a bunch of home routers support it. A number of manufacturers make routers specifically to support that for the people, for the enthusiasts who want to be able to have that level of control. Right? I've used VPN to home. I've had VPN to my house on multiple occasions that I've used. I've had VPN between my house and the school I worked for at Clark College to our lab so that I could remotely administrate stuff from home. I had a site-to-site VPN stuff set up. When you work from home as an administrator, you will have VPN from home. And that's, like, if you're ever on call as an administrator, if you work for an ISP especially, you'll be on call, you'll have VPN access. You'll actually be able to do most of your work remotely from home. A lot of places, you get to work sometime from home. I mean, that's part of the deal. It's like, not only you're on call, hey man, my kid's sick. I got to stay home with him. Can I work from home today? Yeah, sure. You sit in your office at home and you sit there to work tickets and everything over the VPN. You know, companies would, if they can, they love to provide that level of flexibility because it keeps their employees happy. And it keeps them working when they would normally take the day off for their children. So from a company's perspective, yeah, I may not get as much work out of him, but I'm not paying him a sick day. Okay? I'm getting at least some work out of him or her. My sister, she has to work from home all the time because her kid gets sick or something like that. Now her kid's older, so she doesn't do it as much, but she used to, basically work tickets and do customer service for a software company. She does customer service and support for Columbia Ultimate. They make software for like collection agencies and stuff like that for tracking accounts, and that's part of how she does her job. When her kid was sick or something, she'd work from home, and that's more and more common all the time because VPNs, technology, right? The fact that high-speed broadband access has become ubiquitous if you're in a major metropolitan area. The only people today that are really unable to get broadband at a decent speed is when you're in the sticks, when you're living outside, even in Emmett, you can get cable one, you can get good DSL unless you're way outside of Emmett, or in between Emmett and here, then you may have some problems. Like if you're on the hills, if you're on that highway there, and you're up on the hills there as you cross into Gem County, I bet those, yeah, you're way up on the hill. I'm sure you're paying for wireless access because there's nobody running lines out there unless they're paying big money. Yeah. When I first got it here, it was $50 a month for faster than what I was getting at Comcast for $85 a month. And now Comcast was charging $65, but your bill was $85 with all the fees and taxes. And I didn't realize that you could actually have service and not have those fees. Cable One doesn't include any of those fees. It's like the difference of going through a prepaid cellular versus postpaid cellular. Prepaid cellular, you'll notice you don't have a bunch of taxes and fees and everything on your bill. It's if they say your package is $35 a month, then it's $35 a month in prepaid. But when you're postpaid, if they say it's $50 a month, no, it's not. It's like 60 something. There's all kinds of extra fees and stuff they add. Well, guess what? A lot of other companies don't do that. Comcast does. All the cell providers do. But Cable One doesn't. They actually charge you what they say and advertises the bill. Right now, their base service, which is like 100 meg down and 3 or 5 meg up, is $55 a month, and that's what the actual bill comes to when you get it. If you don't rent the modem, then it's $63 or $62 because it's $7 for the modem. Comcast, it will say $65. That's what you will pay, and then when you get your bill, it'll say like 83 something, and you'll have all these taxes and all this other crap. That I was stunned when I came here and realized that wasn't the case. I was also stunned when my car insurance was half. My car insurance was half here compared to, which I don't understand considering how bad the drivers are here. That I would figure it would be more. I mean, there are bad drivers in Washington, don't get me wrong. But the drivers here are pretty awful, man. Yeah, well, California, it's the ego. It's not the driving quality. It's the fact that they think that they are from California and they're better than everybody else and have a more expensive car. You know, it's just like, well, I obviously paid more money for my car, so I get special treatment on the road, right? No, that's not how that works. I just saw a video last night. Rolls Royce, top down. He's going in the shoulder all the way down past all these cars. Yeah, he's just better than everybody else. He's driving and rolls, man. That's how that's how he rolls. And yeah, it's all ego. Like it's all ego at that. It's because the guy probably has rich parents and stuff, has been told his whole life that he can do no wrong. I mean, we had a kid who his defense was affluenza. But his parents are too rich to basically that he wasn't parented well, and so he has no personal responsibility. At least his wife at least his mom got in trouble for that. Because they ran to Mexico, right? Remember, he's got a real weird. I don't know if you followed that one. The guy who he killed a bunch of kids, got killed in the back of his truck and stuff, and they gave him like 6 months in supervised release for killing like 3 or 4 people on the side of the road. And his argument was that he doesn't know right from wrong because his parents are rich, and they never taught him right from wrong. Affluenza was the. Well, and then he got in trouble and basically got busted like drinking and all kinds of stuff on video when he's on probation, and so they were going to revoke his probation and make him go to jail. So him and his mom ran to Mexico, and it's like as close to an incestuous, like weird relationship between the mom and the kid as you can get. Like yeah, oh yeah, it was all over the news last year or like a couple years ago when it happened. This is way off topic. I don't know what's happened to. He's in jail right now. I forget the kid's name. There we go. Affluenza teen, right? Ethan Couch. Ethan Couch killed a bunch of people. So he was like 17. So Ethan Couch, the so-called affluenza teen, mowed down 4 people while he was drunk. Has to serve out the remaining year of his prison term. Of course, this is after he got back after him and his mom ran to Mexico. Right. Oh yeah, they captured him. They got him. They captured in Mexico and deported him up here. So he had originally got 10 years probation for it, and that was it. No jail time. 4 people were killed and 2 more injured in the 2013 accident. He originally dodged jail time after a psychologist testified the then 16-year-old had affluenza, a result of his troubled relationship with his rich parents. There's the truck. Well, no, it was when this happened. If you just go on Wikipedia and read about Ethan Couch, this guy, if you're interested in any of this. But it's amazing, and only in the United States or maybe Saudi Arabia could you get away with a defense like this. Well, yeah, because the sheiks can do no wrong. Like, if you're super rich in Saudi Arabia, your kids can do all kinds of crap and they'll explain it away. There's no accountability to rich people in Saudi Arabia. There's a huge class system in Saudi Arabia, United Arab Emirates, the rich oil countries, the OPEC nations. There's a really, really stringent class system in those countries. And we're kind of like that to some degree here, in that, like, the rich are just in and of themselves a whole different kind of American. Like, they just, most of them don't even have a concept of what working is like, right? Mm-hmm. If yeah, if you're rich, if you're a rich man, if you're from a well-known family, one of the oil families in Saudi Arabia, you're damn well untouchable. I mean, you have to piss off someone above you to get in any real trouble. But again, it comes from history. We'll look at history. Look at how I mean, the whole medieval structure was like that. Okay, you had the people, and they felt that they would lead by example and show, what the low people could never achieve, because they were very stringent. If you were a peasant, you could maybe become a servant of a lord, but you would never achieve. It was all about bloodline, right? And it's not any different in Saudi Arabia, modern Saudi Arabia today. It's all about bloodline, all about your rich family. I don't know how we always get on these topics, but they're always interesting topics. I always find them really interesting, but we get on these and this is always happens to my classes. We get on, I have had some of the most disturbing topics in my class. And you get like 20 minutes into it and you're like, the whole class is sitting there like, how the fuck are we talking about this now? It's like, this is a networking class. How are we talking about cannibalism? How did we get on this? And we'll spend 20 minutes talking about cannibalism, or just God knows what it is. It's always interesting, but but by the time you get to the end of the conversation, it's like, how the hell did it lead here? Same thing on YouTube, though, right? You go on YouTube to watch a video, 20 minutes later, you're watching a cooking show about turtles. You're just like, I don't know how I got here. I just clicked on a couple of videos, and now I'm watching something for the last 20 minutes that's completely unrelated to anything I've ever done in my life, and I have no reason to know this. That happens to me all the time. Me and my girlfriend we'll sit there on YouTube, and 20 minutes later we're watching underwater crocheting, and we had started out looking at boats or God knows what else. Like, it's some awful, awful thing. So I talked about site-to-site. I talked about remote access. Let's talk about dynamic multi-point VPN. So dynamic multi-point VPN allows you to do a hub and spoke VPN. So let's say we got 3 sites and we have the hub. Okay. The benefit is that typically in hub and spoke, for this router here to communicate with this router here, the VPN has to go through the hub and then go back. Dynamic multi-point VPN uses an FH, so what was it? No. Damn, I can't remember the name of the acronym now for it. It's a special server that it uses. It's Next Hop RP. I think that's it. I just can't remember some of these damn things. Okay, so what happens is This is the next top resolution server, okay? And it's used in conjunction with dynamic multi-point VPN. So what happens is this router and this router would have to go through this one. That's not how dynamic multi-point works. Dynamic multi-point will allow, this router will host the NHRP that informs these of the information they need to dynamically build a VPN between the two of each other. So they'll use this to then build a tunnel for this communication so all the traffic doesn't have to go through the hub. But it's almost like a VoIP call. So a voice over IP phone call is kind of like that. You could talk to the call manager. Call manager does the call setup, gives you all the information, but the actual phone call is between the two phones. Okay? They're just direct IP communication between the two phones of the actual traffic. The call signaling and everything is through with the call manager. Kind of same thing here. We can use this as the guide for it to build the tunnels between the sites without them having to send all traffic through the hub. Normally, you can't do that on the fly. You can't typically do that. These are detailed VPN communications, and if this guy wants to talk to this guy, it has to go here and then has to go back. That's traditional site-to-site VPN, and this becomes the hub. With dynamic multi-point VPN, these can dynamically form as needed, where this runs the server that's the guide for the whole thing. So it still acts as the hub, but you're not using the bandwidth of this link to have these two communicate. The data that they send between each other, the setup comes from here, but the actual data that's going in the tunnel goes between only them two, which in a traditional VPN setup would not. You'd have individual site-to-site tunnels to each, okay? So Cisco software solution for building multiple VPNs in an easy, dynamic, and scalable manner. Dynamic multi-point VPN basically builds these tunnels on the fly using a server that's hosting the tables for how all that stuff is going to work. That's the next top resolution. Okay. So GRE. GRE is a very, very simple tunnel. You go on the interface, say, okay, I'm going to be part of GRE. Say, here's the end, here's the beginning. Do it on both sides. That's it. It's reverse. Target source. Well, the target source on this side is the target destination on this side. And the reverse is true. Okay? That's pretty straightforward. Say what type of GRE it is. IP. IP GRE. Okay, so there's only 4 or 5 commands you have to do, but if they're not accurate at all, both parts of the tunnel won't come up. And so what you're doing is the purpose of a tunnel is to create a private path over a public network. So what I'm doing is if I take private messages that have private IPs on them and I put them into an envelope and I call that envelope, I call it GRE, okay, right on the screen up here, okay? I take the IP, the TCP, and the data, and I put it into a GRE packet. That GRE packet has the protocol type and the flags for the GRE tunnel, okay? But it doesn't have any encryption or anything like that. It just says what protocol it's going to carry. In this case, it's going to carry IP, okay? Then another IP packet is put in place. So we put GRE, we put the information about GRE on there, and then we put the IP, another IP packet. The last IP packet, the one here, that's the one that has the public IP address information. So the source IP would be the public IP of the router, and the destination IP would be the public IP of the FAR router, okay? But those are the public IPs. What's in here is the private IP. So we're encapsulating private IP information into a public IP packet, and we have a GRE packet in between the two. And the GRE is what basically tells us how to process this part of it here. Now, GRE is layer 3, meaning GRE can only store an IP version 4, IP version 6 packet. It cannot store like an Ethernet frame. So what happens when we need a VPN type that preserves layer 2 information. So what I'm saying is GRE only preserves layer 3 and above. It does not preserve anything below layer 3. L2TP preserves layer 2 and above. So that's the differences between the two protocols. GRE only supports IP, only supports IPv4 and IPv6, where L2TP supports encapsulation of Ethernet. So you could actually tunnel layer 2 information, for instance, VLAN tags that are stored in your Ethernet frames. So if you only need to do a layer 3 VPN, GRE is the choice. If you need to do a layer 2 VPN, we typically are going to use what's called L2TP, and we're actually going to do IPsec over L2TP instead of IPsec over GRE. And that's just, do you want L2TP stuff? Do you want layer 3 stuff? Imagine having the same VLANs at two physical different locations and a trunk link that goes over the internet. Okay? You can do that with L2TP. I can extend my switching to go over my WAN with L2TP. With GRE, I can't do that. I extend my layer 3 to go over the internet to another side, but I can actually extend my VLANs and everything from one site to another with L2TP. Now, do we use L2TP a lot? Only when needed. Okay, it's not something you're going to need a need to do that, because are there drawbacks to these, to any of these, to IPsec, to GRE, to L2TP? Hell yes. MTU, maximum transmit unit. My maximum transmit unit is 1500. So I take something that's spec'd for 1500 and I put it in a GRE envelope. And I put that GRE envelope in another IP. Guess what? I'm no longer at 1500 anymore. I'm above that. I now have to fragment, or my traffic could get dropped. So I have to lower the MTU on my network to compensate for this. So when we deploy VPNs of almost any type, we have to look at how much overhead that they're generating and shrink our IP packets so they'll fit in that 1500. Otherwise, your VPN gets dropped by the internet. Okay, so that's one of the drawbacks of this. As soon as we add encryption, as soon as we add that integrity checking and encryption, we add additional overhead. Okay, there's additional packets that have to be sent. Plus, there's additional CPU cycles that are used in the encryption and the integrity algorithms that we use. Okay, so GRE. Generic routing encapsulation, okay? It handles multi-protocol and IP multicast traffic between two or more sites that only have IP connectivity. So GRE works over the internet quite well, but the thing that GRE doesn't do is it doesn't do encryption. That's where we would have to add IPsec on top of it, okay? So IP tunneling using GRE enables network expansion across a single backbone. This is what we do. We take the original internal IP packet, we put it into a GRE packet that has a flag and a protocol type, and we put that into a new IP packet that has the external public information of the internet on there. And then when we get to the other side, we strip off the internet information, strip off the GRE, and put it back into the private information, and we're able to move private information over a public network. So the IP address here, that can be a 10, that can be a 172.16, that can be a 192.168. Okay? The IP address here cannot. The IP addresses here must be public internet accessible IP addresses, where these can be public or private IPs. Usually they're going to be private. Okay? So, how do we set up GRE? We create the tunnel interface. Okay? So we're going to say interface, tunnel, and then a number. Interface tunnel 1. We go to the IP address, and we configure the IP address on the tunnel interface. Okay? This is normally a private IP address. So you have your public interface, and you're going to tie your GRE tunnel to that. Your public interface is the one that's connected to the internet that has all your public information. Okay? You create a new tunnel interface that has the private information on it. Then you specify the tunnel source IP address and the tunnel destination. Now, typically when we're doing the tunnel source, we can do it by the name of the interface. So I can say the tunnel source is S000. Okay? That means the IP address on that interface acts as the tunnel source IP, and then the tunnel destination can be an IP address or a name. Okay? So we can set up a name if we wanted. Let's see. Let's pull up Packet Tracer here. So when configuring GRE, this is what we need. I'll put this up on the screen here. It's loading. It's just being very slow. Okay, so here's an example where I have an internet connection and I want to build a private GRE tunnel between these two routers. So as far as the routers are concerned for the tunnel, they're essentially directly connected to each other. So when the traffic enters the tunnel, it doesn't see any of this stuff. That's all agnostic because it's encapsulated. It's just writing in it, so it doesn't see anything that's going on in this exterior network. For all intents and purposes, the routers see it as one hop. So when you do a trace route, it's going to look weird. It goes in the tunnel, it comes out of the tunnel. But it's not going to show anything in the trace route of the tunnel. You have to trace outside of the tunnel to do this. Now imagine that tunnel being encrypted. You can't see what's in the tunnel. This is where troubleshooting VPNs becomes a nightmare. Okay, you have to get in the tunnel to see the traffic. So your entry point where you're doing Wireshark and stuff has to be on the device that's creating the tunnel. It's very problematic. You get no visibility. Well, with GRE, we don't have to worry about that. We can see all the GRE stuff in Wireshark. There's no encryption involved. Okay, GRE doesn't do encryption. So here what we're going to be doing is we'll go into here, we'll go into router, and we're looking at S00 is our link. Okay. Oops. Okay, so enable. Let's do a quick shell run. We should have all our networking set up. So we have our serial interface there. Okay. Let's see if they did any host addresses. So one thing I can do, so here's one of the things that I've never showed you before. Okay, but they do mention it. They mention something in the book that I don't like. The way that they get into it's DNS resolution. So instead of putting an IP address, I can put a name that equals that IP address. Normally, we would do DNS resolution, but we typed in no IP domain lookup. That turns off DNS resolution. So on Cisco devices, you can do DNS resolution on the machine itself. It's called IP host. So IP host, we will say RB is the IP host, and we give it the IP address. Okay, so now RB is going to be 10.10. We'll do the 209. So 209.165.122. I'm assuming it's going to be 2, but we'll look on this. Okay. What I'm looking for here is this number, .2. Okay. So now, for instance, I can type ping RB. Okay. So they show an example where the tunnel destination is a name. This is how they're doing this. That's how they're pulling it off. But is that extensible? I have to go on every single device and type that IP host command to get that to be on every device. Otherwise, what we really do in the real world is we set up a DNS server with this information and we actually point it to the DNS server. So instead of doing no IP domain lookup, we actually do IP domain lookup and put in the server number and put it in the DNS server. And so it goes to a DNS server to resolve all that. And so we don't get those errors or anything, right? It's just beyond what we need to do. But I saw it in the book, and I didn't want you guys to get confused when you're reading that. Because all of a sudden, out of nowhere, it doesn't tell you how to do this command, but all of a sudden, nowhere, it's assuming you know how the DNS resolution is all set up and working. So I don't like that at all. Okay. Okay, so let's go ahead and do the setup for GRE. So what we're going to do is we're going to create the tunnels. So first, I have connectivity, but notice my trace route. Okay, so if I trace, let's do it this way. Can I ping 192.168.2 dot whatever this PC is? What do we got for the IP here? 2.2. Okay, 2.2 is my IP. So if I go here, can I ping 2.2? Unreachable. What that means, these pings aren't going through, and what that means is this here doesn't have a route from this network to get to this network. And the reason for it is only the external networks are being routed. The internal networks are not being routed. Okay? That's because we got to get GRE going to be able to have that take place. So right now, notice that I cannot ping this PC here. I can't get to it, and I won't be able to until this is set up, and that's because of some of the routing they've got going on over here in this little cloud. Right? There's a bunch of devices here that they have locked that we can't get into. So let's go ahead and create the GRE tunnel. So we're config T, and we're just going to do interface tunnel 1. Okay. So now we have a tunnel interface, and then we're going to go into the tunnel, okay, tunnel 1. Okay, so now we're in the tunnel, and we're going to go tunnel mode. Okay, so we can do GRE or IPv6 IP, IPv6 over IP encapsulation. Wouldn't want to do that. We're doing GRE, and we're going to do IP. So it's GRE over IP is what we're going to be doing. That's the default tunnel mode anyway, but we're going to set that. Tunnel mode, GRE, okay, and then we do tunnel source. Okay, specifies the tunnel source address. So in this case, the source address is 000. Okay, or we could take a look. So if I want to do, another way to look at it would be do show IP int brief. That'll show it to me. And the tunnel is this serial interface. So this IP would be the tunnel source. So I could go ahead and say tunnel source. I could do it S000. I could do 64.103.211.2. What if you change it? What if you change the IP on the S000? Okay. Makes a lot more sense to do it this way. Okay. Now I need a tunnel destination. Now the tunnel destination needs to be a name or an IP address. Okay. So in this case, we want tunnel, tunnel destination. Okay, and we need to give it an IP address. And that tunnel destination, okay, is going to be the IP address given here, right? So that's the 209.165.122.2 is the destination. So when we're saying tunnel source, tunnel destination, that is going to be the public IPs, okay? Now my tunnel interface comes to up. Now it's not going to go fully up. Now I need to add an IP address to the tunnel. This is going to be, the IP address for the tunnel is going to be the internal IP address. So IP add 10.1.1. Or no, we're doing 10.10.10.1. 255.255.255.252. Okay? So we're doing a /30, just as it states right here. That's what I'm typing in. Okay? So now the tunnel's not going to be up because we haven't completed the other side. Okay. Now, I may also need to create a static route, depending on how all this stuff works. See, we have a static route here. Okay. The problem is I'm going to need to make a route for this other network to be able to get over the tunnel. So notice here we have tunnel 1 is connected, but where is that 209 network, the 209, right, or the 192, see here how we have this? Okay, here's the issue. You see this 192.168.2 network, how does this know to get over here? So we're going to have to make a route to that, but first we want to finish the tunnel. Okay, so let's take, before I go do that, let's go back over here, show IP int brief. Okay, so we've got, notice tunnel 1 is up. Okay, let's see if the other side is how it's configured. Okay, so now we need to basically do the same thing, configure T int tunnel 1. Okay, so I made my tunnel interface, tunnel source, or no, excuse me, tunnel mode GRE IP first. Tunnel source is going to be S000. Okay, tunnel destination is going to be whatever that IP address is right here, this one here. Okay, so it's going to be the IP address of S00 on this side is going to be our destination because we're going from this side to this side. So here's the end. And so that's going to be 64.103.211.2, 255.255.255. Nope, never mind. Okay. And then we need to do our IP address, and that's just going to be 10.10.10.2, 255.255.255.252. Okay. Now, the question is, does the tunnel work? Ping 10.10.10.1. Yes, it does. Okay. We haven't set up the route for the remote network, but the 10 network is locally connected now. Okay. So if we do show IP route, we'll see that the 10 network is locally connected to tunnel 1. So we can ping anything in the 10 network that we're directly connected to. So I can verify the tunnel is up, but what I can't do, where's 192.168.1.0? Okay, so if I ping 192.168.1.2, still not going to work. Why? Because it's not going in the tunnel. It's not going in the tunnel. Okay? So what I can do is I would need to I would either need to have a routing protocol, which we're not doing over here, or I would need to do a route. So IP route, and the network that we're messing with is 192.168.1.0, 255.255.250. Okay, but what would be the exit interface? Tunnel 1. Okay, so tunnel 1 is the exit interface for this. Oh shit, it doesn't let me do the tunnel 1. Tunnel 1 would be your exit interface. It doesn't actually let me specify it in here. So what would be the other one? Next hop, right? What's the next hop? 10. Okay, we're telling it the tunnel, so we're using the private IPs. So 10.10.10.2, right? That's the other side of the tunnel. Oh, 1. Yeah, I'm on RA. RB. Okay. So that would work. So now, if I do show IP route, I now have this one right here. Okay. That means that one network, this router needs to know about this network, and this router needs to know about this network. Okay, and they need to know that they need to go through the tunnel to get to that they can't go out to the internet and get to it. So the way this particular works with GRE, see with IPsec, we don't have tunnel interfaces. You have to use ACLs to mark the traffic. In GRE, it creates tunnel interfaces, and those tunnel interfaces can then be routed to through routing protocols and through static routes. So it's actually a lot easier to do that with. So we can do IP route and then 192.168.2.0. That's the network on the far side. Okay, and then we're just going to do that IP address. So our next top IP, which is 10.10.2, where the other one was 10.10.1. So now can I ping 192.168.2.2 on the other side? I can. Okay. So now watch if we go to a trace route. So now PCA should be able to ping PCB because I've built that tunnel. So I can ping 192.168.2.2. But notice, okay, just going to ping. Worked fine. So, but notice I'm pinging a private network that I'm not directly connected to. My connection is going out on essentially the internet and coming back. And it's doing it because it's going through the tunnel I've created. So now let's do the trace route is what we really want to see. And this is where you're not going to see a bunch of public IPs. You're going to see mainly private IPs. There we go. So did it leave? Did it leave the private network? According to this, it never did. According to my trace route, this thing thinks it's completely connected to a private network and it never went out on the internet. But the reality is it totally went out on the internet. That's how it works. That's what the tunnel does. Okay. The differences in the tunnel is, do we encrypt it? Do we password it? Do we do the other stuff? Those are the other protocols that we use. IPsec, SSTP. There are many, many flavors of VPNs. Some of them are inherently broken. Some of them are broken if you don't configure them correctly. Like for instance, SSL was broken. You want to use TLS. You don't want to use SSL anymore. In IPsec, you wouldn't want to use DES or 3DES necessarily. You'd want to use AES. Those kinds of things. Questions about tunneling? Does it make sense what it's accomplishing? Is it clear on what we're accomplishing? Okay. Is it clear on how we're doing it? We're saying let's form a small private tunnel, okay, and we're going to use that private tunnel to send private traffic over the internet with. And we just need to say, okay, where does the tunnel end and begin? Well, it ends and begins at the public addresses. Begins and ends at the public addresses, and then we say, what are the private addresses that are used for the tunnel itself? That's how we specify those. Okay. So how do we verify GRE? Extremely easily. So show interface tunnel. So show interface tunnel 1 is going to verify the information. Show IP interface brief. And if we're running OSPF over our tunnel, we could do show IP OSPF neighbor, and it would show our neighbor. So really, like in that instance, I was using static routing. I wasn't using OSPF. I could totally form neighbor adjacencies of OSPF, and guess what? That means your OSPF is going over the internet. But the internet never sees it as OSPF. But it is going over the internet. That's the beauty of how this stuff works. Okay? So the last thing we're going to cover today, and I'm gonna go pretty quick over it. I love how this slide is so wrong. Varieties of spanning tree protocols. Okay. Spanning tree, not spanning tree. Just random spanning tree header slide in there for no. Okay, so Pppoe. Pppoe is, it's again, we're tunneling stuff. Okay, we're making a PPP connection over Ethernet, And this is mainly used in DSL today, in business DSLs. So we make PPP private connections and stuff over business class DSL. So how it works is we have our normal IP packet, but then we're encapsulating that IP packet into PPP, and then we're encapsulating it into an Ethernet. Okay? So what are we doing with this? PPP is used for all serial links for dial-up and ISDN. Okay? DSL, we use either Pppoe or PPP over ATM are the two most common for the way we do DNSL connectivity. Now, is that PPP link, how far does that PPP link really go? It only goes to the ISP. It terminates at the ISP. So it's not like a PPP link that's going from my Seattle office and terminates at my Portland office. That's not how we use Pppoe. So the benefits of PPP is it supports CHAP. So the reason we use this is we can then add authentication to a DSL connection. DSL in and of itself does not have an authentication process for it. So by adding PPP, we can add authentication on top of that. Ethernet links do not natively support PPP. PPP over Ethernet provides a solution to this problem. PPP over Ethernet creates a PPP tunnel over an Ethernet connection. Okay? So this is what we're doing with, and they have a really good, they do a better job in the book. The book has a better layout for this stuff and has some better graphics than what my slides have. Here's how it works, is that you have to create a dialer interface. You have to create your 3 different interfaces. You have to create a layer 1 interface, a layer 2 interface, and a layer 3 interface. Okay? The layer 1 interface is your dialer, and you have a template that you have set up with the dialer. So you do interface, dialer, and you set a number for it. And this is where you're going to set up Pppoe, and you're going to create the dialer pool. Okay? Let me see. I can't bring that up. Why don't we take a quick break? We'll take a quick break. Let me pull this stuff up, and then this is the Pppoe stuff is the last stuff I'm covering for today. You guys will have labs for the rest of it, okay? And then tomorrow, the only thing we're covering really is SDN and Internet of Things and maybe some troubleshooting. I got it. I got this stuff up on my screen. I needed to. I forgot I installed Redium. If you guys ever need the ability to read EPUBs and stuff like that, you can install Redium. Redium is a free plugin for Chrome. And so you just open Chrome and click on your apps button here, and you click on Redium, and you have Redium. And it's an EPUB reader and stuff for, instead of installing like Adobe Acrobat or any of those, you can just use Redium. So I'd forgotten I'd done this on that machine. I installed Redium. So where is it here? Where's Pppoe? Private WANs and VPN. So they have, unfortunately, I just don't have good material on Pppoe. So there's a couple things here that describe it so much better than what the slides that I have. And so that's why. So here's what covers the GRE stuff and DMVPN. That's all covered in that chapter as well. But then it gets into Pppoe. That's what I'm trying to find here. Dynamic multi-point VPN. All right, here we go. I just realize this is a little small. But mainly what we're looking at here is the graphics. All right, so here's an example of kind of what we're setting up. Is we're going to set IP packets, but we're going to build a tunnel between the customer site and the ISP. And in this case, these are DSL modems that we're using, as this is going to be the most common usage of this in modern stuff today. Okay. Now, traditionally, we did essentially this with dial-up and ISDN, but today we're doing it with other stuff with DSL. Okay. However, the DSL connect often connects to customer device, piece of router. They're just talking about that. Okay, so you set up the dialer. So let's go through this. Look closely at this stuff here. So the layer 3 details are in the dialer. Okay, so interface dialer. We put IP address negotiated. That means that the IP address is not going to be statically assigned. We're going to set a pool. We're going to set a pool attached to the Pppoe dialer to be able to assign addresses. Okay, we need to set the MTU down to 1492. Otherwise, we're going to break the tunnel that PPP is creating. Will make the IP packets too big across tunnel and stuff. Okay, so we're going to shrink the MTU. Then we turn on PPP, and notice we're setting CHAP. CHAP hostname Fred, CHAP password Barney. Okay, that's how you send CHAP information when you're using like Radius on the other side. You're not using the host name and stuff like that. This is how you send it. And then we create a dialer pool. Okay, and the dialer pool, you're going to add a client pool to it. I'll show you that. That's what this stuff up here is. Okay, and then we do an interface, no IP address. So the physical interface doesn't get an IP address. The layer 3 information is on the interface dialer. Okay, on the physical interface, we go Pppoe client dial pool number 1. So we bind it to dialer pool number 1, and we enable Pppoe. Now this command is just to set the MAC address for this, and then no shutdown. So this is the process that we go through for this. Okay, and they do a pretty good job. There's one here. So this is kind of how this is bound. So this graphic up here really helps demonstrate where we're doing the commands and what they're accomplishing. So for the layer 3 information in the dialer, we put in the IP address and the MTU. And so we're going to say the IP address is negotiated. And at layer 3 on the physical interface, we just say nothing. Okay? So all the layer 3 information for the connection is on the dialer, not on the physical interface. On the dialer, we set encapsulation to PPP. We set all the PPP information. Okay? Notice we're not saying PPP authentication. We're sending information. We're not requiring authentication. The other side would be configured to require authentication for the PPP link. Okay. And then at layer 2 on the interface, so on Gigabit Ethernet 01 in this particular example, we're just going to turn on Pppoe. So we just enable Pppoe, and then we associate the dialer pool to that interface. So we know what pool to draw from. Okay? So we build all of this, and this will tie it to this, where we create the dialer pool, and then we bind that pool to the interface. So here's another example of how we config in a kind of a checklist. Okay? So you're going to go, here we do, use the interface dialer number. Okay, that creates the dialer interface. We then create the pool number. Use the dialer pool number interface command to refer a pool of Ethernet family interfaces that can be used for a Pppoe. Okay. And remember, like, we could go to many gigabit interfaces. We could have many of them participating in this pool and go into these and add them so they're all in pool number 1. That's a pool of interfaces that are allowing for this communication to happen. Okay? So we go into, we set the pool right here. Now we go into the physical interface and we say it. We go ahead and say Pppoe enabled, and we set Pppoe client dial pool number 1. Now I believe when you set Pppoe client dial pool number 1, Pppoe enable automatically comes into existence. Like that command is automatically applied when you do the other one. Some commands are like that. There's a handful of commands that do that. Okay, then we go into the dialer, we configure PPP, the host name, and we do Pppoe enabled on the Ethernet interfaces. Okay. iOS adds the command automatically when the Pppoe client interface subcommand is added, right? So that's done automatically. We set the IP address is negotiated. We set the MTU, so it'll work over this. And we do not set an IP address on the Ethernet interface. That's how it works. So this here is a really important graphic, is how we're binding this together. We bind the dialer interface with a pool number to the Ethernet interface by that pool number. Okay? That creates a virtual access interface for us that binds the layer 1 and 2 to the Ethernet interface, and that's what forms our Pppoe session. Okay? So if we look at this, dial interface and Ethernet interface are associated by referencing the same dial pool number in the configuration. Okay? So that's how that works. That dial pool number is what ties these two together. Some part of iOS must act to implement PPP and the Pppoe specifics. Call this part of the iOS and Pppoe session as represented on the far right of the figure. Okay, so 1 and 2 to basically come together to form the Pppoe session. We go up and it binds to those, right? Okay. Then kind of go into how to do the shell commands and stuff for it. What are you expected to know for Pppoe? Okay. Setup. Do we have any labs? Do you guys have any labs on that other lab thing for Pppoe? Did you see any? Then IP address negotiated would not be what's in there. It would say IP address and give you the IP address that you're supposed to have. Every client would get its own static IP, a unique static IP. That's not the question you're asking, though, is it? What do you explain the question a little bit better so I understand what you're asking me? Okay. I'm assuming you would put it to a different dialer pool for the people that are getting statics. They would be a member of a different dialer pool than the other one, right? Because so you're creating a bunch of virtualized interfaces across. So you should be able to bind a physical interface to a different dialer pool that has different settings. Because one of the things that we're not getting in this is we're not getting the circuit identifiers that come with DSL. Okay, that's another aspect of this that isn't part of this because we're not. They're showing Pppoe as more of a dial-up kind of thing, and ISDN. Well, in ISDN and dial-up, you don't do static IPs in dial-up. It's all dynamic, so it's all negotiated. You wouldn't really have that. And what you would do is you would have Pppoe, you would have the IP address possibly configured in Radius, and Radius would feed the tunnel that information. Okay. So a lot of times in Radius, if we have username authentication in Radius, we can tie settings to that account. So and I don't know 100% sure. I'm not very good in Pppoe, but I'm assuming there is a way to do that, where to push this out instead of to the local username database and stuff, to push it out to Radius. I don't know if it actually has the capability to pull the IP and use it, but I would assume it does, because otherwise an ISP would have a terrible time keeping this set up for a bunch of business users that have static IPs. It'd be difficult to set it up that way, unless, now keep this in mind, here's one way to do this. The MAC address is something you can set for the tunnel. You can set for the Pppoe connection, you can set the MAC address. Well, when we do DHCP, we bind it to a MAC address. It is possible that how they're doing the IP assignment in that instance is they're actually doing reservations on a DHCP server bound to that configured MAC address that they have set for the Pppoe connection. So the virtual Pppoe connection is assigning its own MAC address in that case. So there's a couple different ways that I could foresee them doing. I don't know the exact answer of that. There's definitely, you can bind things to a MAC address and a reservation. That is a way where someone would get the same IP every time. That'd be one way to do it. The other way to do it, I'd have to dig deeper into. I'm not sure if that's how it works, but I would assume that it can pass the information from Radius to the PPP connection and force it to do that, because we've used Radius to feed stuff into PPP connections forever for authentication. I don't see why we wouldn't be able to feed the IP for that as well. Because Radius can feed VLAN information and all kinds of stuff for an account when you check it. It just depends on what you configure to check for, right? They spend a lot of time here in Pppoe, guys. And the chances of you getting much questions, this is a topic that is covered, but it is very lightly covered on the exam. There's no labs. Okay. So I really wouldn't expect too much in Pppoe. We've always taught it, and they've added more to it, but I've rarely seen any stuff for it. So CCNA, routing and switching, 200.125. Okay. So if we do CCNA 200.125, that's all in one test, and we can do Pppoe. Here you go. Here's a 10-minute YouTube video that goes through the setup of what I just talked about. Okay. So if you need, and what did I do? I searched for CCNA 200.125, which is the all-in-one exam, and I did Pppoe, and this is going to be the stuff we're going to need for that. So right here, we have one. Which part of Pppoe server configuration contains the information used to assign an IP address to the Pppoe client? The dialer interface or the virtual template interface? They're saying A, the virtual template interface. Okay. So these are the questions that we get. There are 3. During which phase of the Pppoe is PPP authentication performed? The PPP session phase, the phase 2, the active discovery phase, the authentication phase, the phase 1. The PPP session phase. PPP is where CHAP happens, right? What phase in PPP would we call that? We don't call it phase 1, we don't call it phase 2. Phase 1 and phase 2 are terms that we use with IPsec, not with Pppoe. The PPP session phase that we're talking about would be the LCP session during PPP. Okay. Which type of interface can negotiate an IP address for a Pppoe client? The dialer. Okay. Really? That's weird. That shouldn't be on there at all. Pppoe is not supposed to be part of ICND1 at all. Okay, so I like how this one says server configuration contains used the IP address to negotiate is in the virtual template, but then it says which type of interface to negotiate an IP address. It says dialer. So one of these two questions is wrong. Okay. So here we have the same kind of questions. So here it looks like the PPP session phase. Okay. So what I'm not seeing is it looks like there are only like 3 questions in the test bank for that. Okay. I wouldn't sweat it, man. I'd really be focused on other things that are going to be much more prevalent. Okay? If you guys are PPPoE is one you're not expected to understand a lot about it. Read the book. Hopefully some of what I've said helps with that. I'm definitely not. That's one of my weaker areas is PPPoE because I don't use it. I never worked the DSL that we used. I never had to mess with that stuff. That was never something I really messed with. And dial-up, how many people really mess with dial-up today? If you work for an ISP, you may, but other than that, chances are you're never going to touch dial-up again in your life. Okay, chances are really good that you will never use dial-up again. If you've been on broadband for a few years now, chances are you'll never go back. And businesses are at the point now where wireless is ubiquitous. It's everywhere. So there's no need to have our people dial up all the time. They can go to a Starbucks and use a VPN, and it's much faster and much better. Easier for us to manage. There's so many things that are superior with that. Okay. So that's all I have for today. Tomorrow, we basically have a little bit of troubleshooting that I'm going to go over debugs. I'm mainly going to show you how to use the debugs. The only way to get good with debugs is to play with them yourselves. I can sit here and explain them. You're going to fall asleep and you're going to forget it, so it's not worth spending a lot of time. But I'll show you some more of the debugging tools to play around with. And we're going to do SDN and Internet of Things. So we'll talk about network programming and that kind of stuff, and that's it. We're done then. So we'll probably have quite a bit of lab time tomorrow. We may go over some test questions tomorrow as well. And then Wednesday, we'll be going over test questions and just doing labs and studying the whole time. And then we're done, at least with my involvement. Of course, if you guys have questions or need resources or something, just send me an email. Yeah, you all have my email address. Feel free to send stuff to me. Okay? Other than that, go ahead and take a break and then work on labs for the rest of the day. I would do this GRE lab. This GRE lab is pretty good. It's nice and simple.